Welcome to this deep dive. Today we're looking into efficient local inference of large language models and specifically focusing on Llama.cpp.
That's right. We're basing this on the Go developers Masterclass document, aiming to really pull out the key research, the practical methods, and, the important takeaways for tech professionals.
Especially developers.
Wow.
And we want to understand the real-world applications too.
Definitely. LLMs are increasingly vital, but deploying them efficiently, that's a real hurdle.
Especially on, say, consumer hardware, right?
Yeah.
Not everyone has a massive GPU cluster.
Exactly. And the source material positions Llama.cpp as a very compelling solution for that exact scenario. It helps perform those complex LLM computations locally.
Which is crucial for many applications, and especially relevant for Go developers, as you mentioned in the document.
Go is fantastic for scalable systems, but that heavy numerical processing for LLMs, that's typically outside its core strengths.
So Llama.cpp, being written mainly in CC++my, kind of bridges that gap.
Precisely. It lets your Go applications tap into local LLM power. So maybe we should start with how it achieves this efficiency. The document highlights its modular architecture.
Good starting point. Let's unpack that architecture.
Okay. So it's deliberately modular. The idea is separating concerns, which helps with both efficiency and maintaining the code long term.
Makes sense. And the foundation is this library called GGML.
Yes, GGML. Think of it as the core math engine. It's built specifically for these kinds of AI computations. It handles the low-level numerics, tensor management, memory allocation.
And the memory part is interesting, right? It minimizes runtime allocations.
It does, yeah. It takes a specific approach there we can delve into later. But crucially, GGML also supports various hardware backends.
Like CPU, CDA,
All of those, yes. CPU, CUDA, Metal, OpenCL, Vulkan. It provides that abstraction, and it defines and executes the computation graphs, basically the steps the LLM takes.
Okay, so GGML is the engine room. Then on top of that, you have model-specific logic.
Exactly. This layer knows how to run different LLM architectures.
Like Llama, Mistral, Falcon.
Those are great examples. It implements their specific forward pass, how they process input using the building blocks, the primitives provided by GGML.
Primitives like matrix multiplication, attention mechanisms, the core LLM operations.
Right. Understanding that this layer adapts GGML's power for specific models is key to seeing why Llama.cpp is so flexible.
Got it. GGML provides the power, this layer directs it. But how do you actually get a model into this system? That involves the file format, GGUF?
Spot on. GGUF is quite important. It's a binary format.
Right.
It packages everything together, the model weights, the vocabulary it uses, other metadata, all in one single file.
Which must make distribution and loading much simpler.
Hugely simpler. The source material really emphasizes this. And there's a specific module, the file format handler, that reads these GGUF files, parses them, and gets the data ready for GGML and the inference logic.
And I imagine there are tools to convert models into GGUF.
Yes, that's part of the utility side supporting practical use.
Okay, so it's not just the core engine. The examples and bindings seem important for developers actually using it.
They really are. They act as the interface. Your document probably mentions Llama.cli, the command line tool.
As a direct way to interact.
Right. But there are also server implementations, and crucially for our audience, language bindings. The Swift example is often mentioned, but the Go bindings are obviously key here.
They show how to integrate it, provide templates.
Exactly. They abstract away some of the C++ complexity.
And then there are the utility modules. What role do they play?
Think of them as handling supporting tasks. Things essential for the workflow, but not part of the main inference calculation itself.
Like quantization, model conversion.
Precisely. Quantization, converting models from PyTorch or TensorFlow, and even grammar parsing, constraining the output.
Grammar parsing for structured output, like JSON.
Yes, exactly. There are often examples like Python scripts to generate a grammar from a JSON schema. These utilities really extend what you can do.
So it sounds like all these modules, GGML, the inference logic, the file handler, examples, utilities, they're all designed to work together cleanly.
Very much so. GGML is central, naturally. But there are well-defined interfaces between all these parts. The file handler feeds data, the logic uses GGML, the bindings talk to the higher levels.
And that modularity allows for independent work, optimizing one part without breaking others.
That's a major benefit, yes. It helps with development, optimization, and contributes to the overall robustness and flexibility that developers value.
Okay, that gives us a good picture of the architecture. Now let's shift focus to the core functionalities. What actually happens during inference?
Right, the core processes.
Yeah.
Well, fundamentally, as we touched on, it starts with loading the model from that GGUF file.
Efficiently reading the binary, parsing the headers, getting the weights.
Exactly. And speed here is important for application startup. GGUF is actually optimized for this, sometimes using memory mapping for even faster loading.
Okay, model loaded. Then you need to process the input text, tokenization.
Correct. LLMs don't work on raw text. Tokenization breaks the input down into numerical tokens.
Looking up words or subwords in the model's vocabulary.
Yes, mapping them to unique IDs. That sequence of IDs is what the model actually sees. Llama.cpp handles this internally.
And then the inference engine kicks in, taking those tokens.
But in doing the heavy lifting, the forward pass of the neural network, it uses the loaded model weights and GGML's compute power to figure out the probability of what the next token should be.
And this is where optimizations like multi-threading or GPU offload happen.
Exactly, to speed up this really computationally intensive part.
Now, for conversations or long inputs, maintaining context is vital. How is that handled?
Context management. LLMs have a limited context window, a maximum number of tokens they can consider.
Right, a fixed size.
So managing this efficiently is crucial. Llama.cpp uses what's called a KV cache.
Okay.
It stores intermediate computations from tokens it's already processed. So when generating the next token, it doesn't have to recalculate everything from scratch for the whole sequence.
Which saves a lot of computation, especially in ongoing dialogue.
A huge amount, yes. It's critical for performance in those scenarios.
And then we get to the actual text generation.
Which is usually iterative.
Yeah.
The model predicts the next token based on the probabilities.
Appends it to the sequence.
And repeats, predicts the next one, and so on. Your source might mention different sampling strategies here.
Like greedy, top K nucleus.
Those are the common ones. They control how the next token is chosen from the probability distribution, affecting the output's style creativity versus predictability.
Interesting. And one advanced feature mentioned was grammar-based output constraints. That sounds really useful.
It is, for certain applications. It lets you force the model's output to follow a specific structure.
Like ensuring it produces valid JSON.
Exactly that. Or any other defined grammar. It's incredibly useful for extracting structured data reliably, or maybe for implementing function calling in a structured way.
The JSON schema to grammar example really highlights that power.
It does.
So it all fits together. Efficient loading, tokenizing input, running inference with context management via the KV cache, generating text token by token, maybe with grammar constraints.
And all powered by GGML doing the math efficiently across different types of hardware.
That really clarifies the core workflow.
Yeah, that integrated pipeline is what makes Llama.cpp such a practical tool.
Okay, let's dig into the why behind some of this. What's the underlying design philosophy? The source seems to emphasize certain principles.
Absolutely. The core philosophy seems to boil down to minimalism, performance, and portability.
Okay.
And a big part of that is the CPU-first optimization strategy.
Meaning they prioritized making it run well on CPUs initially.
That seems to be the case. While GPU support is strong now, the initial focus was broad CPU efficiency, making LLMs accessible on more common hardware. This meant really optimizing using SIMD instructions.
It's like AVX for x86, Neon for ARM.
Exactly, squeezing performance out of standard processors.
And the minimalism aspect relates to dependencies.
Right. By building core things like tensor math and memory management into GGML, they avoided pulling in lots of large external libraries.
Which simplifies building it, integrating it.
And reduces the final library size. It's a leaner approach which helps with deployment.
Of course, the choice of CC++ itself speaks to performance.
It does. It gives that fine-grained control over memory and computation needed for extreme optimization. It is perhaps a bit of a barrier for developers used to other languages, but it's key to the performance.
Does the source material point to specific software design patterns being used?
It suggests a few, yeah. Within GGML, you see data-oriented design principles focusing on memory layout for speed.
Okay.
The computation graph idea is itself a pattern, allowing optimization of the calculation flow. And the layered architecture we discussed earlier.
GGML, model logic, bindings.
Yes, that's a classic pattern promoting maintainability and making the system easier to extend.
So bring this back to Go developers. How do these choices affect them when they use something like Go Llama.cpp?
Well, understanding this helps. Those Go bindings typically use the foreign function interface pattern FFI.
Wrapping the C++ functions.
Exactly. The goal is to keep the super optimized performance critical code in C++A, but expose a more Go idiomatic API.
So the Go developer focuses on application logic, concurrency using routines.
Right. And they delegate the heavy LLM number crunching to the efficient Llama.cpp backend via the FFI bridge. It's about leveraging the best of both worlds.
That makes sense, combining Go strengths with C++ raw performance for this specific task.
Precisely.
All right, we've covered architecture and philosophy. Let's get into the really deep technical stuff, the specific features driving that efficiency as detailed in the source.
Okay. One of the absolute headliners here is quantization. We mentioned it briefly.
Reducing the precision of the numbers.
Exactly. Taking those high-precision floating point weights and activations in standard LLMs and shrinking them down, often to 4-bit or 8-bit integers.
Which dramatically cuts down model size and memory needs.
Dramatically. Essential for running on phones, laptops, edge devices. But the clever part in GGML is not just storage. It includes highly optimized kernels that compute directly on these quantized, lower precision numbers.
So it's not just decompressing and then computing. It works with the smaller format.
Yes, minimizing the performance trade-off. It's a sophisticated implementation.
And you mentioned memory management earlier as being unique, the pre-allocated buffer.
Right. Instead of constantly asking the system for small bits of memory during runtime using malloc or new,
Which can be slow and fragmented.
GGML tends to allocate a large, contiguous block of memory upfront.
For all the tensors and calculations.
For a significant portion of them, yes. This avoids the overhead of frequent dynamic allocations and deallocations. It leads to much more predictable, deterministic memory usage, too.
Which is good for resource-constrained systems.
Very good. Then there are the optimized kernels themselves.
The actual code doing the math, like matrix multiplies.
Exactly. These aren't just standard implementations. They are heavily optimized, often hand-tuned for specific hardware.
Targeting those SIMD instructions we mentioned,
Yeah.
EVX, NeoIn.
Yes, and also leveraging the different GPU backends, CDA kernels, metal shaders, etc. They really focus on maximizing the throughput of these core operations on whatever hardware is available.
And concurrency. How is that handled internally?
Primarily through multi-threading for CPUs. Tensor operations are broken down into smaller chunks that can run in parallel across multiple CPU cores.
Making good use of modern processors.
Absolutely. And as we said, Go developers can then add another layer of concurrency on top with goroutines when managing multiple requests or integrating into larger systems.
And the support for multiple hardware backends. CDA, Metal, OpenCL, Vulkan, that's quite comprehensive.
It is. GGM acts as an abstraction layer.
Yeah.
You write the computation graph once, and GGML figures out how to run parts of it, or all of it, on the available GPU via the appropriate backend.
Offloading the heavy compute.
Right. And there's even that sophisticated hybrid CPU plus GPU mode.
For models too big for the GPU VRAM.
Exactly. It intelligently splits the work, running some layers on the GPU and others on the CPU, making even huge models feasible locally.
Finally, the GGUF format design itself seems engineered for efficiency too.
It is. Consolidating everything simplifies distribution, as we said, but it's also designed with things like memory mapping in mind.
Meaning the system only loads the parts of the file it actually needs into memory.
Potentially, yes. It allows for more efficient loading and memory use, especially for large models, avoiding loading the entire thing if you only need certain parts immediately.
So it really is this combination. Quantization, smart memory allocation, super optimized kernels, concurrency, broad hardware support, and an efficient file format.
All working together. That's what delivers the performance that makes Llama.cpp so practical and powerful for local inference.
Okay, let's wrap this up. Based on the document, what are the main takeaways for technology professionals, especially our Go developers listening?
Well, the big one is that Llama.cpp is a serious, highly efficient option for running LLMs locally, right inside your own applications.
Moving away from reliance on cloud APIs, potentially.
Exactly. For Go developers, it provides a clear path to embed this powerful AI capability directly into their systems. And the technical features we just discussed, quantization, memory management, optimized kernels, those aren't just details, they're why it works so well on everyday hardware.
And this capability unlocks new possibilities for developers, doesn't it?
Absolutely. Think about it. Building applications that are more private, that work offline, that have lower latency because the AI is right there.
Desktop tools with built-in AI smarts, on-device NLP for mobile apps.
Or backend services where data residency and speed are paramount. For Go developers, it means combining their skills in building robust concurrent systems with cutting-edge AI, all locally managed.
This is a really compelling vision. So maybe a final thought for our listeners, particularly the developers tuning in.
Yeah, definitely. Based on what we've discussed from this material, really consider how could integrating local LLMs using tools like Llama.cpp fundamentally change the user experiences you build?
What new features or workflows become possible in your specific domain?
Exactly. It's worth exploring this technology further. It really does have the potential to reshape how we build and interact with software.